Hey, welcome back. So, today it's been kind of rainy and muggy, and so my wife can't really take out the babies for me to record. So, it might turn out that there's a good deal of yelling in this video. I'll try to edit around anything I can, but yeah, there's not much you can do when you have two 2-year-olds. I mean, house isn't big enough to like hide me away in some soundproof room. We have bookshelves up and the room's pretty cluttered. I don't know if I included that in any videos, I hope not. So it might be, it might dampen it down a bit, but we'll see. In any case, the goal today is to record a whole bunch of homework exercises and stuff like that to help you guys get ready for the exam. I didn't want to put this off any longer because, well, I mean, the exam's on Monday. I still need to figure out Proctorio. I have no idea how that works, but likely you'll have to have a webcam or camera with your laptop or something set up for it. I try to avoid using it as much as possible, and that's why I make the quizzes for online classes open book, and so then there's just no point in having Proctorio there. Homeworks, I mean, you do it on your own time, so I mean, obviously nobody's putting a webcam on you. But at some point I have to ask you to do everything without a book, and the only way to make sure that happens is using Proctorio. So it's the unfortunate consequence of being in this pandemic and having to do everything online. Yeah, I don't know. It seems a little bit Big Brother, but yeah, that's just the way it goes. In any case, so there's a lot of things that people have been asking about, since the first lecture. I've been answering questions piecemeal whenever somebody asks me, but I might as well put everything in one place for those people who haven't really been bold enough to ask. So one of the things that people have been asking about is, how do you determine if something's linear? So maybe I didn't make that clear enough in the first lecture, and so I'd like to address a few of those problems here. Then there's been a bunch of questions about direction fields, Picard Iteration. That last question I put on Picard Iteration, don't worry about it, that's not going to be on the exam. That is really just something to make you stop and think. It's a challenge question, if you'd like. But it would take way too long to perform on the exam, and so I wouldn't ask you to do it there. Let's see, there are some questions that are more qualitative, like why would you do Picard Iteration? And I can answer that right now, and the answer is because it gives you an approximate solution when you might not have any other tools at hand. So I guess it's a little early for you guys to know this, but I mean, basically you're going to learn almost all the techniques that we have to solve a differential equation in the next 2 weeks. It turns out that most differential equations can't be solved in a nice closed form, and for the most part you're stuck with approximations. So we can solve things like separable differential equations, we can solve things like linear differential equations, and a handful of others. And there's some techniques that we're not going to talk about, like power series techniques and recursion relations and a few things. But on the whole, if you're given a random differential equation, you're not going to be able to solve it. And so all you're going to be left with are your sort of qualitative and quantitative tools, the tools that we just learned. You have, say, Picard Iteration is one way to attack a problem. Euler's method is another way. There's other things similar to Euler's method, like Runge-Kutta, but it's really sort of beyond the scope of this class. I think I gave you some code on Canvas if you want to play with it, and and then there's also the direction fields, which are really good for one-dimensional problems. Where you just have one independent variable, one dependent variable. But for higher dimensions, that becomes harder and harder to interpret. So there's other analysis tools that people develop, like Lyapunov methods and things like that. But again, we won't cover those in this class. But basically, you're getting the bulk of the tools that most people use in order to pick apart a differential equation. The only thing that we're not really covering much in this class is stability theorems. But if you go on to take a system theory class or a control theory class or something like that, you're going to talk about that a lot. So Picard Iteration is another thing that we're going to talk about. People wanted me to go over some questions concerning direction fields and isoclines, and I can see why those can be tricky, and so we'll go over those. And And then a few examples of Euler's method. We'll throw it in there just to try to, to round out everything. Because we haven't really talked about that very much. It's only really one algorithm, and you'll have to do like 2 or 3 calculations. So it's not too bad. I wouldn't worry about that too much. Just make sure you remember the algorithm itself. But yeah, so I guess there are 2 algorithms you have to memorize. So you'd have to memorize, say, Picard Iteration, and you'd also have to memorize Euler's method, and we'll review those in a minute. And then you just have to be able to do isoclines and direction fields, right? So that's another thing. Out of section 1.2, the trickiest part there is implicit differentiation. So I gave a video already sort of reviewing how to do implicit differentiation, and it's really something you should go back and double check. I'll try to throw in an example here if I have time. But yeah, that is an important thing. And then otherwise, just definitions. So linear differential equations, nonlinear differential equations, PDEs versus ODEs, everything out of section 1.1. And I think those are the more challenging bits that are going to come up on the exam. And so we'll try to talk about them now. Anyway, so before there's a screaming fit or something like that, I better get going. And I hope it helps. Okay, so welcome back. So today we're going to be talking about, say, homework 1.1, 1.2, from 1.3 and 1.4, and then also a little bit of Picard iteration. I obviously can't work on everything out in, like, say, 45 minutes or an hour, so I'll do my best to talk about maybe some of the more difficult problems if I can. Let's see. So out of homework 1, homework 1. For section 1.1, this was problems 1 through 15. And this was mostly just definitions, right? For instance, they were asking us, in, say, problems 1 through 12, they were asking us to find, to determine if, say, the given differential equation is, say, linear versus nonlinear. They wanted the order. They wanted to know if it's an ODE versus a PDE. And find the independent and dependent variables. Okay, so we can talk about a few of those. I think the one that's confusing most people is I'm trying to figure out if something is linear. So what does it mean to be linear is the question. Basically if we have, say, a linear first order equation, it would basically be like this. So it would be A of t, say dy dt, if dependent variable is y and the independent variable is t, plus b of t, say, times y of t is equal to c of t, right? So this would be, and usually we don't write y of t, right? We just write y. So this would be, say, a linear first order ODE. That's what this would be. If we go up to second order, it would be something like this: a of t d squared y over dt squared plus b of t times dy dt plus c of t times y is equal to d of t. Just whatever these functions are. The key thing is that you have these guys each on their own, and the only thing that's really attached to them is a of t, b of t, and c of t. And also significantly, we can't have, say, y squared, we don't have, say, square root of y, we don't have 1 over y. All of these wouldn't be linear. So this would be, say, a linear second order ODE, right? And for each of these, we have the dependent variable is y and independent variable is t. right? I think that would be everything they're asking, right? Yep. Oh, and yeah, so that would actually be all they're asking there. So let's take a look at, say, one or two examples. So let's take a look at, say, number 3. So number 3 is, say, dy dx is equal to y 2 minus 3x divided by x times 1 minus 3 y. So right away we see that the dependent variable is y, and that's because it's happening here in the derivative. Our independent variable is x, and so that's because it's happening right there. Is an ODE, and that's because there's only one independent variable. And now the question is, what is this order? So it's first order. That's because the highest derivative appearing here is just the first derivative. Now the question is whether or not this is linear. So we do have this guy in the bottom, and that makes it not linear, but I mean, maybe that's not clear yet. So what I can do is I can just multiply the denominator of both sides, and that might help. So if you just declare this as non-linear, that'd be fine with me. But say dy dx is equal to y times 2 minus 3x. If we distribute this, we get x dy dx minus 3y dy dx is equal to, say, 2y minus, well, let's keep this 2 minus 3x times y. Okay, so now let's take a look at a few things. So we're basically looking for it to be of this form, right? It's a first order. This is what all first order linear differential equations look like. And so here we have a dy dx and it's attached to some function of x. That's okay. That would still fall within the realm of being linear. Over here we have a y times 2 minus 3x. 2 minus 3x is a function of x and not y, so that would be fine too. But here's where the real sticking part is. We have a dy dx times minus 3y, and that extra y here times dy dx means it's not linear. So we can say now it's not linear, right? Okay, let's take a look at another example. Just looking for something interesting. Okay, how about the first one? So problem number 1, they have 5d squared x over dt squared plus 4 dx dt plus 9x is equal to 2 cosine of 3t. All right, so here our dependent variable is x, our independent variable is t, is an ODE because there's only one independent variable. Let's see, second order, and that's because second derivative appears here. Now I'm going to tell you that it is linear, and that's because it fits the form we're looking for. This guy, the second derivative of x with respect to t, has a function that's constant, so it's just a constant function if you want. So this would be like a of t. That's fine. It doesn't involve x. That's all we care about. Ditto here. So we only have a 4. Doesn't involve x. Good. Move on. 9 doesn't involve x. Okay, we're good. And is equal to cosine of 2 cosine 3t. Doesn't involve x. So good. So we actually have a nice linear differential equation. So that's all we're looking for. All right. Let's see. Another problem. Maybe looking at slightly different. Let's see. Here, number 4. Let's see. So we have du dx squared plus d squared u dy squared is equal to 0. This is Laplace's equation. So our dependent variable is u. Our independent variable is x and y, and so that means that this is a PDE because we have 2 independent variables. It is second order. The highest derivative here is 2.
And they didn't ask us to write this, but I will tell you it's linear. But specifically what they say is that not to worry if it's linear or not, if it's a PDE, and I won't test you on that. It turns out that the equation that they give us for linearity, this is a specialized version just for ODEs. There's a more general one that applies for PDEs, but we're not going to talk about it because this class is all about ODEs. Okay. One last. Let's see. So take a look at number 5. So we have y of 1 plus, say, dy dx squared is equal to c. Let's figure out our dependent variable, which is y. Our independent variable is x. And our is an ODE, because there's only one independent variable. And it is first order. Don't be fooled. This 2 has nothing to do with the derivative. Okay, so and is nonlinear, and that's because we have squared dy dx. And so, and if you want, you can even multiply everything out. You can say this could be y plus y times dy dx quantity squared is equal to c. And so you can see that maybe if you want, y is attached to a function of y, and so or the function of derivative of y, whatever. If it's not a function of x, so it is nonlinear. Okay, cool. So I think I'm going to leave that there. Let me see what else is in there. They want us to write differential equations that fits. Okay, so let's take a look at number, say, 14, right? So here we want to write a differential equation that that fits the description, and so they say that the velocity at time t of a particle moving along a straight line is proportional to the fourth power of the position. Right, and so they want us to write that. So the velocity at time t of a particle, so I'm guessing, so let's just say x is a position. All right, and so if it's position, then velocity is a derivative. So we say x prime is equal to, well, it says is proportional to the fourth power of the position. So k will be a proportionality constant, and x to the fourth power, and that would be that. And so proportionality really just means you put in some k or whatever, and so that's what you get. All right, so that's section 1.1. All right, so section 1.2, let's talk about that. 1.2, and I think I'm really going to focus mostly on the implicit derivatives, but we're going to 1 through 12. I said odd. I really do all of 1 through 12 if you have the time. 14, 16, 23, and 27. These are the ones I listed. Let's take a look. So, okay, so basically a lot of these we're trying to show that these things are explicit solutions or implicit solutions to differential equations, and see, and they say determine if, etc. Let's see. Okay, so let's take a look. All right, so they want us to show, so problem 1, A. Well, actually, I don't like problem 1. Let's do problem 2. Let's do problem 2B. So 2B. So it wants to show that xy cubed minus xy cubed sine of x is equal to 1 is an implicit solution for dy dx is equal to x cosine of x plus sine of x minus 1, all of this times y, divided by 3x minus x sine of x, and they give us an interval on the interval 0 to pi over 2. Why would we include that interval? Well, when we have, it's probably just because we're going to be kicking out zeros out of the denominator. So, yeah, certainly. So if sine was pi over 2, it's 1, and then we'd have x minus x roughly, and then that gives us a 0, right? So, so yeah, we're restricting to this interval, and just because that's where we exist. Okay, so how do you start? So we start off with this guy, xy cubed minus xy cubed sine of x is equal to 1. All right, so what I'm going to do is I'm going to take the derivative with respect to x, so dy by dx. And remember that y is a function of x. So y is a function of x. So it's not a constant, it's something we're going to have to use chain rule, product rule on. Okay, so on this first term, what is it going to give us? Well, dy by dx on x is just 1, and using the product rule, so we're going to have just say 1 times y cubed plus, now we leave x alone, and then we're going to have 3y, and then by chain rule, we have 3y squared, and then by chain rule, we have dy by dx, right? Okay, so that's the first term. Now the second term, it's going to be really annoying, actually. It's like a triple product rule, if you like. So basically we have the derivative of the first, and then we leave these guys alone, and then we have the derivative of the second, and then we leave the other two alone, and then we have the derivative of the third, and we leave the other two alone. Or if you want, you can take the product rule and just do it inside, so you just treat this as one function, take derivative of this, leave this alone, take derivative of this, which involves another product rule, and leave this alone. But I'll give you the same answer. Okay, so that's just sort of a faster way to go about it. So how do we do it? So we take derivative first, it gives us 1 times y cubed times sine of x, plus the derivative second, so we have we have again 3y squared times dy dx times sine of x, rather than leaving the third alone, plus x times y cubed, and we take derivative of the third one, so that's cosine of x, right? And now this is equal to 0, because the derivative of 1 with respect to x is 0. Okay, so now we're trying to see if we can work it into this form, and really the best way to do that is just go ahead and factor out all of our dy dx's and move everything else over to the other side, and then we divide, right? So everything that has dy dx, let's see what we got. So we have 3xy squared, and then we're subtracting a 3xy squared again, but this time times sine of x, right? And everything else I'm going to move over to the other side, so we're going to get minus y cubed minus, actually plus a y cubed sine of x, and then we're going to have a plus x cubed cosine, x times y cubed cosine of x. Okay, now we divide, so we get dy by dx is equal to minus y cubed plus y cubed sine of x plus xy cubed cosine of x, all over 3x y squared minus 3x y squared times sine of x. Okay, now clearly we can pull out a y squared out of the bottom and a y out of the top, so that's going to give us y, and on the top we're going to be left with sine of x plus x cosine of x minus 1 and this divided by, say, we're going to have a 3 times x minus x sine of x. All right, now let's look. Is that what we have up here? And indeed it is. So yes, it is or the given equation. All right, it could be explicit, right? So the given equation implicitly defines a solution to the given differential equation. Say 1b is another good example. So show that phi of x is equal to e to the x minus x is an explicit solution to dy dx plus y squared is equal to e to the 2x plus 1 minus 2x times e to the x plus x squared minus 1. Okay. All right, let's do it. So what do we need? Well, we have phi, but now we need phi prime, right? So phi prime is going to be e to the x minus 1. Now we plug everything in. This looks like a headache, but let's go into it. So inside of dy dx goes phi prime. So it's going to be e to the x minus 1. And now we're adding plus phi squared, right? So it's going to be e to the x minus x squared. Now what we're hoping is that we can work this into something like this. So at this point, I'm just going to ignore the right-hand side and hopefully see what we produce if that actually matches up. So we have e to the x minus 1 plus, here we're going to have e to the x squared, so e to the 2x, minus 2e to the x times x, and then plus x squared, right? That's what we get. Let's see. So it looks like they have an e to the 2x here, and then we have an e to the x. Let's go ahead and see if we can factor that out. So our e to the 2x, we're going to move out to the front, just like what they have. So we have e to the 2x. And now we have a e to the x minus e to the x times negative 2x. So that's going to be plus e to the x times 1 minus 2x. Right? And now we have this guy, plus x squared, just all on its own, and then minus 1. Now if we take a look, that is exactly what we have here. So yes, phi is an explicit solution to the differential equation. Okay, so I mean that's basically the idea, and sometimes it's not actually going to be a proper solution to a differential equation. So yeah, let's see. I'll give one example where it's not going to work, not to give away the answer. But yeah, so we have x equals cosine of 2t is 1, and we have that dx dt plus tx is equal to sine of 2t. I'm pretty sure this won't work, but let's see. All right, so we want to show that this is not going to work. They don't tell you that, but I am sort of putting the cart before the horse and telling you the answer. Okay, so first of all we need x prime. So we need dx dt, which is going to be minus 2 sine of 2t. And now we plug everything in. So we get minus 2 sine of 2t plus t times x, which is cosine of 2t. And the question is it equal to sine of 2t? Well, if it was, truly we could just simplify this left-hand side until it was sine of 2t. But the issue here is we have a t here, and that's not going to work. And so there's no, it is not a solution. If you wanted a more explicit answer for that, just look at something like this. So if I take, these have to agree on all t, so if I say consider t equals something I can compute, say pi over 2, then I see that it's going to be minus 2 sine of 2 times pi over 2 plus pi over 2 times cosine of 2 times pi over 2. And what I see on the left-hand side is that this is going to be minus 2 times sine of pi, which is 0, plus pi over 2 times cosine of pi, which is negative 1, right? And so this is equal to negative pi over 2. But on the right-hand side, I see that I have sine of 2 times pi over 2, and that's just 0, right? So there's a point where they don't agree, so they can't be the same function. So left-hand side and right-hand side disagree at t equals pi over 2, so not the same function. Right, so there you go. So that's an example. If you wanted to just get to this point and declare that they are not the same, that's fine with me. But if it helps you understand it a little bit, this is how you more formally would demonstrate that they're not the same function. Okay, so now let's take a look. What else? All right, so that's a lot of the more difficult parts out of these sections. 23 and 27. What are these? Determine whether or not. Oh yeah, we should probably talk about that. Okay, so I kind of bungled the quiz for like half of you. Halfway through the day, I realized I had an error. So on quiz 2, I forgot to put does not guarantee a unique solution, and then I gave exactly the wrong answers, and it seemed to confuse a lot of people, and I had fronted a lot of emails. But yeah, let's see. So so basically we're going to try to determine if theorem 1 implies the existence of a unique solution for the following initial value problems. Okay, so start off with 23. So we are given dy dx is equal to y to the 4 minus x to the 4, and we're told that y of 0 is equal to 7. So if we take a look, where is y of 0 equals 7? So it's x of 0 and y of 7, so 1, 2, 3, 4, 5, 6, 7. Okay, and so then what we need to do is we need to figure out is f of xy, which is equal to y to the 4 minus x to the 4, continuous at 0, 7? And the answer is yes. It's a polynomial. Then you ask, is the derivative of f with respect to y, this is how it's written in Calc 3 if you've taken that, is equal to 4y cubed. Is this continuous at 0, 7? And the answer is yes. It's polynomial. And so, therefore, if you want to be fancy in math, yeah, that's a symbol for therefore, the initial value problem is guaranteed a unique solution by theorem 1. All right, that's what we would say. Okay, let's take a look at one that maybe isn't so clear-cut. What problems did I ask? 27. Let's see. Okay, yeah. So 27. It's a good one. All right, so let's see. So here we're given y dy dx is equal to x, and at y of 1 is equal to 0. So if we look at this, our initial value problem is starting at x equals 1, and we're at 0, so this is 1, 0. And we need to simplify this and put it into standard form, right? So we get dy dx is equal to x over y. And so then you can ask, is f of x xy written as x over y continuous at 1, 0? And the answer is no. It's not even defined there. Zero, it's a divide by 0. So that's it. So it's not guaranteed a solution. So it's not guaranteed a solution by theorem 1, a unique solution. Okay, so yeah, that's how you do that sort of thing. Yeah, I apologize for the confusion on quiz 2. It's been a rough week. I've been doing a lot of childcare. My wife was sick, so I had to do a lot more of that, and so I was only able to work and get these things done either during baby nap times or like in the middle of the night when I was dead tired. So hopefully I'll try to be more strict to myself as far as writing questions, especially for the exam, so we don't have any hiccups like that. Okay, cool. Let's see about section 1.3. Let's go ahead and graduate to that. So I was in homework 2, and in particular, a lot of people were asking questions for some of the latter problems. So it's like draw the isoclines with their direction markers and sketch several solution curves. 11 is maybe not the best one to start at. Let me see, what did I actually ask for? So 1.3, we're looking for problems 1 through 5 and 11 through 14. Let's see what 1 through 5 are. Yeah, these are okay. I don't think these are actually all that bad. I think I have some of these in another video, so I'll link those to you guys later. But let's take a look at problems 1 through 14. That's what we're going to focus on right now. 11 through 14. I really don't like these. Let me give you better ones. Let's do 15. Yeah, 15 would have been a better one. These are actually all terrible. The reason why these are all terrible is that the isoclines that you get out of these are straight lines. So they end up being very, very confusing, especially when you're supposed to put slopes and then you have a slope of that line, and those aren't even related. But if we take a look at number 15, that might illuminate things first. So let's take a look at 15. So we have dy dx is equal to 2x squared minus y. And I think this is actually a collection of problems that maybe Nagle, Saff, and Snider kind of choked on a little bit. All right, so we're trying to find a curve for the solution to the initial value problem here by using isoclines with direction markers. So let's try to be very careful about that. So I'm going to try to put everything, let's see if I can draw a straight line this morning. There we go. And there we go. Okay, so, all right, so our initial value is here. So we should probably put some, figure out some slopes in the area, but we'll just poke around, see what we get. So in red, I'll put all my direction markers, and isoclines I'll put in green. So we need to figure out what is isocline for, say, the slopes that are all, say, 0. That's a good place to start. And so this is going to be 2x squared minus y. So 0 is going to be my slope for the markers the dashes I'm going to put there. And then we see that this should give us that y is equal to 2x squared. So my isocline then is going to be a parabola, upward facing parabola. And on that upward facing parabola, all my slopes are 0. So these get horizontal hashes. Okay, so now let's go to the next one. Let's take a look at, say, dy dx is equal to, say, 1. And so it's going to give me 2x squared minus y. And again, 1 is my slope, right? So now this tells me that we're going to have 2x squared. Well, let's actually move. So we have y is equal to 2x squared minus 1. Right, so this parabola is going to be the same parabola, but just shifted down by 1. Right, something like that. And so then all of these guys are going to be at sort of like 45 degrees. And so you just try to stay disciplined and keep a consistent slope all the way across it. Although it looks like these are a little shy of 45, but you get the idea. The general idea that I'm looking for is that this is steeper than this. Right? Okay, and let's find another one. Let's find dy dx is equal to -1, which is equal to 2x squared minus y. And so we have, sorry for all the yelling, at least it's happy yelling, that's a nice change. So we get y is equal to 2x squared plus 1. All right, and so now we shift up. And so go up by 1, and then we get there. And so these all have -1 tick marks. You just do enough of these until you get sort of an idea of what's going on. And so, let's see. Let's do one more. And basically, I'm noticing that my initial condition is going to go off in this direction, and then it's going to kind of shoot up. And I kind of want to see what happens as it gets a little bit further. And so I think that if I choose, say, dy dx is equal to, say, -2, or say positive 2, I should get another answer in that direction. So it's going to be 2x minus y. And that tells me that we're going to have y is equal to 2x squared minus 2. So we shifted down again, and it's going to be something like this, except now we have a steeper solution. And so it should be steeper than the last one, and so that's basically what I'm doing here. And so now if I just go ahead and try to draw a solution, so here, this first isocline says go horizontal, and so we're going to go horizontal, and this one says go up, they go up, this one says go up steeper, and so we go up steeper, and then likely we're going to keep going up steeper than that. And that's it. That's what we get. So that's the solution to the differential equation. Okay, cool. So this is what we get there, and let's take a look at number 11. Now, and I'll show you why this ends up being a little confusing. So we have dy dx is equal to, say, minus x over y. This actually corresponds to a circle, I think. And so we're told then that we're looking at y of 0 is equal to 4. Okay, so let's go ahead and take a look. All right, so say 1, 2, 3, 4, and this is where we're going to start. And now let's go ahead and start drawing some lines. So 1, 2, 3, 4, 1, 2, 3, 4, 4. Okay, so let's draw some isoclines. So let's figure out dy dx is equal to 0. Say in red. Then what do we get? We get minus x over y, and then that tells us that, well, if I multiply over by x, that tells me that x is equal to 0. So so all the points where x is equal to 0, we have a horizontal line. All right, so my first isocline for that slope is this, and so basically our slopes are 0 all along here. I'm not going to put a mark here at the origin, just because we would be divided by y, and that's undefined. So we'll leave that alone. Now let's take a look at, say, dy by dx is equal to, say, 1. And so this is going to be in red. And what do I get? So now I get minus x over y. That tells me that y is equal to negative x. Right? So so this is this line. So this line itself has slope -1, but the slope field here is all going to be positive 1. So it's going to be like this. And if we go ahead and do, say, dy dx is equal to, say, -1, so minus over y, that tells me that y is equal to x, right? And so so in this case, we're going to have this line here, and we're going to have hash marks being -1, so we're going down like this. Right. Okay, and it's starting to look like a Christmas decoration. Okay, let's see. Just get a better idea. So let's say dy dx is equal to, say, 2 minus x over y. It tells me then that y is equal to minus 1/2 x. And so that means that we have a line like this. And the slopes there are going to actually be very steep. It's going to be steeper than this one. And so make sure you just keep that nice and relatively bigger. And it's going to be the same slope all the way up. Okay. And then if I do, say, dy dx is equal to, say, -2, what do we get? Well, that's going to be minus x over y is equal to, and that's going to give me y is equal to 1/2 of x, right? So, so that's going to give me that right here. And so -2 is going to be steeper down, like that. Okay, so now I can get sort of an idea of what's going on. Basically, yeah, I'm going to just say that this guy basically goes on like this and then goes down steeper, and yeah, that's the idea. You could even draw it the other direction if you want. I typically don't like saying that because I think of your initial point as being the starting point, you go to the right. But the book sometimes asks you to go in the other direction, so it's not unreasonable. But I guess I come from systems theory and controls a lot of times, so we think of just, yeah, our independent variable is almost always t, so that just moves forward in time. Okay, so yeah, so that's the idea. So the reason why this one would be more confusing, and a lot of the other ones in there are actually more confusing, and maybe I should have just included 11 to 15, is that all of these are going to be like, say, straight lines or vertical lines or horizontal lines for 11, 12, and 13, and even 14. They're all going to be straight lines for your isoclines, and that gets confusing. And so that's a really weird thing for them to have done, and so you know, be prepared for you know, other sort of things, and so so yeah, things like polynomials, for instance, can come up on the exam, and I think I did a couple other examples in the lecture. So hopefully that clears up that section. Let's see, what else? Euler's method. All right, so this is going to be section 1.4. So here we're given problems 1 through 5, odd, and 9, 12, and 15. Let's see what they are. So let's say 1 through 5, odd, 9, 12, and 15. And let's see. So 1 through 5 just wants us to use Euler's method on these examples and just march forward. And yep, same for 5. 9, what is 9? Use Euler's method to approximate solution to initial value problem on this interval. Compared to the actual solution equals 1, y equals -1 over x. Yeah, that's fine, you can do that. 12, what was 12? 12 was a fun problem, kind of a challenge problem. If you don't get that, I'm not going to put that on the exam. But yeah, it basically shows you that the differential equation that gives you Euler's method also gives you the classical sort of finance version of the number of e, which is 1 plus 1 over n raised to the n. That actually came out of that formula actually came out of compound interest formulas back in the 1600s when they discovered e in particular. That was one route. They actually discovered through 2 routes. Another one being trying to find the area under a curve of a hyperbola, which would be 1 over y equals 1 over x as an example. But yeah, and then 15. Looks like I didn't actually include that in the picture that I took for you guys. But yeah, that's fine. Don't worry about it. Let's see. I'm just going to do number 5, and I'll do that for 2 steps. All right, so we're basically want to use Euler's method to approximate the solution to y prime is equal to x minus y squared with y1 equals 0 with step size h equals 0.1 at the points x equals, say, 1.1, 1.2, and they gave more, but I'm stopping there. All right, so let's go ahead and figure this out. So our y of 0 here is going to be 0, and our x of 0 is equal to 1, right? Our h is equal to 0.1, they gave that to us, and f of xy is equal to x minus y squared. So if I go ahead and I start off, I want to figure out what y1 is. And now y1 should be roughly equal to y of 1.1, right? We're moving h steps past where x of 0 was. So y1 is going to be equal to y of 0 plus h times f of x of 0, y of 0. And so this is going to be, say, 0 plus 0.1 times f of x naught, which was just 1 comma 0, right? And so we know that is 0 plus 0.1 times, looks like 1 minus 0, and so then it's going to be 0.1, right? So that is y1 is 0.1. Y2, and y2 should be equal to, or roughly equal to 1.2, and so that's the idea. This is going to be y1 plus h times f of x1 comma y1, right? And so what are we going to get then? Well, we have 0.1 for y1 plus 0.1 for h, and then we have x, which is now 1.1, minus y, which is 0.1 quantity squared. Right? And this is as much of arithmetic as I expect you guys to be able to do on the exam. So it's 0.1 plus 0.1, no calculators on the exam, by the way. So just do this by hand, of 1.1 minus 0.01, right? Okay, that's not bad. So it's going to be 0.1 plus 0.1 times 1.10 minus 0.01, so it's 1.09. And so this is going to be 0.1 plus 0.109, and this is going to be equal to 0.209, right? And so that would be y2. So these are my answers. So this is going to be, say, y of 1.1, and this is y of 1.2. Right, so I don't want you using calculators on the exam, but I'm not going to give you anything difficult. So at most you should be multiplying, 0.1 times, say, 1.1 or say 1.09. These are all fairly straightforward. Okay, so that's good. Let's see. So let's talk about some Picard iteration problems, and then we'll call it a day. And so let's see. So we're posted in modules. And we have lecture 3 notes. Picard, oh, not the M file. Picard iteration homework, there we go. Okay, so let's see. So for, so first of all, so we have Picard iteration. But the problem 5, I'm not going to put on the exam. Don't worry about that. I'll make a separate video and just talk about how to do it. It takes some time. But yeah, so let me just work out, say, problem number 2, and I'll do 2 iterations. Right, so let's see. Or rather problem 1. People ask about problem 1. So let's say, so problem 1 gave, say, dy dt is equal to 2t minus y squared with y of 0 is equal to 1. So we're selecting phi naught of t to be just whatever y naught was. So that's just this. Now phi 1 of t is equal to, say, y naught plus the integral from 0 to t of, say, 2 tau minus phi naught of tau squared d tau, right? And so this is going to give me 1 plus the integral from 0 to t of 2 tau minus 1 d tau. All right, so if we integrate that, we get 1 plus, now we have tau squared minus tau, evaluate at 0 and t, and at 0 this is 0, so that can go, we can don't have to worry about that, so it becomes 1 plus t squared minus t. Right, so we can plug that into tau 2, and so we get y of 0 plus the integral from 0 to t of 2t minus phi 1 of t squared dt. And this is already becoming a pain in the butt, so we get y naught was just 1, and now it's integral from 0 to t. Oh, and that should be a tau on the inside, right? Internal variables, don't mix them up with your external variables. Good programming habits, by the way. So 2t minus, looks like we're going to have 1 minus t plus t tau minus tau squared. And this quantity squared, d tau, is equal to 1 plus the integral from 0 to t of 2 tau minus, all right, let's see, figure this out, 1 minus tau plus tau squared times 1 minus tau plus tau squared, and basically we're looking for all combinations. You could also just distribute this through to all three of these and then distribute again. There's a whole lot of ways to handle this. All right, so 1 times 1, so basically I'm going to match each of these guys, collect those terms, then I'm going to collect all of these terms multiplied by each other, and all these terms multiplied by each other. That's how you can do this. So it becomes 1 minus tau plus tau squared, so that's 1 times it. Then we have minus tau plus tau squared minus tau cubed, and then for the last one we get plus tau squared minus tau cubed, and then we get plus tau to the 4. Right, and so all together we have 1 all by itself minus 2 tau, and then we get plus 3 tau squared, then I get minus 2 tau cubed, and then I get plus tau to the 4. And if you know you did it right if your coefficients are all symmetric. Okay, so now we get 1 minus 2 tau plus 3 tau squared minus 2 tau cubed plus tau to the 4th d tau. And what do we get then? It's 1 plus, all right, so it's going to be tau squared over 2, so that leaves tau minus tau plus tau squared. I'm distributing the minus sign at the same time. Then we get minus 3 over, actually not minus 3 over anything, it just becomes tau cubed. That's nice. Plus 1/2 tau to the 4, and then we get minus tau to the 5th over 5. And this is valued at 0 and t, so then we get 1, I can go ahead and combine these two guys at least. So that's going to be plus 2t squared minus t cubed plus 1/2 t to the 4th minus t to the 5th over 5. Then we subtract off by 0, that term disappears. Okay, and if we want to keep everything sane, I'll just move these guys over, and so we have a nice ascending power. Okay, so that's how you do that Picard iteration. Now there was one question that was slightly different on the quiz, but it really just comes down to integration. And let me pull up the quiz real quick so I can answer that. And I'll give you another example of where that can come from. Didn't mean to make it a trick question. It was just it's a nice little simple exercise. So take a look at the quiz. Let's see. Okay, we are So for the initial value problem, where we have dy dt is equal to 2y with y of 0 is equal to 1, what is the result of Picard iteration if we, so what happens if phi naught of t is equal to e to the 2t instead of what we usually use, which would just be y of 0. Okay, so that's easy to see. So basically, let's see what happens. So we have phi 1 of t is equal to, say, y of 0 plus the integral from 0 to t of 2 times phi naught of tau, right, d tau. And this is going to be 1 plus the integral from 0 to t of 2 times e to the 2 tau d tau, because we're using this guy. And so just go ahead and integrate that. So it's 1 plus, pull out a 2, e to the 2 tau over 2, evaluate 0 and t. And so 2 cancels this one, and so we have left with 1 plus e to the 2t minus e to the 0, and so e to the 0 is just 1, so you get e to the 2t back. So the answer is e to the 2t, or it returns itself. And so yeah, that would be the result. And this is what happens. This actually means that this is actually the solution to the differential equation. That's what happens. You get what we call a fixed point. But yeah, it's a really simple integration where you just have to integrate e to the 2t. So not too bad, but I'm sorry if it caused any confusion. A more complicated one that I was going to put on the quiz, but then I decided just to make it a little bit easier. I was going to ask what would happen when you have dy dt is equal to 1 plus y squared, y of 0 is equal to 0, and let phi naught of t is equal to tangent of t. This is a little bit more fun, but maybe not great for a quiz when it might catch you off guard. So, but basically you got phi 1 of t is equal to, say, y of 0 plus the integral from 0 to t of, say, 1 plus phi naught of t squared dt, or d tau, right? So this would then be equal to 0 plus the integral from 0 to t of 1 plus tangent squared of tau d tau. And then you ask, well, how do I integrate this? Well, this would be integral from 0 to t. Use Picard, he used Pythagorean identity, right? So this actually is just secant squared of tau d tau. And so then this gives me secant, so then it gives me tangent of tau integrated at 0 and t. And so this is tangent of t minus tangent of 0, but tangent of 0 is 0. So again, tangent of t is actually a solution to this differential equation, so it actually pops out itself. Okay, so hopefully that covers everything you guys were wondering about, and it makes things a little bit clearer. I apologize for any yelling or singing or laughing and things like that. We have a joyous household that can get quite noisy with two-year-olds. So, but yeah. In any case, let me know if you have any more questions. I'm happy to answer anything else. You've seen everything that's going to end up on the exam. I'm not going to put anything tricky. Didn't even mean to make this last problem tricky. It just, I guess it tripped up a few more people than I expected. But that's okay. Quizzes aren't worth a whole lot of points. And in any case, moving forward, I'll be sure not to do that again. Okay, so let's call it and go back to my office.
All right. So that was probably like over an hour. I actually recorded this other one back to back with my opening, so it always seems like, hey, yeah, I'm back. But it's been like 3 seconds for me. But knowing myself, it's probably going to take about an hour or hour and a half to go through all these problems. And hopefully it doesn't take that long. I'll try to put some links to other resources I've developed over the past year. The exam one from my fall and spring semester were a bit different than this one. We're in a different sort of situation, and so that means that we cover a slightly different material. So yeah, so in particular, I didn't have any Picard iteration on exam 1 in fall and spring, and I included section 2.2 on separable differential equations in there on exam 1 previously, but it's not going to be on this exam. So if you go back and you watch those, just keep in mind separable differential equations is not going to show up. Anyway, my hair continues to grow, so now it's in like a full apex, including my bangs. Maybe one day I should probably cut it, but that's quarantine. I should probably clean this up a little bit, look slightly more professional. But yeah, anyway, hope it helped, and good luck on the exam 1 in a couple days. All right, take care.